Hey everyone, welcome back to my Calculus 1 series. In today's lesson, we're going to go over the definite integral. So just a recap from what we learned in last lesson, one of the main things that we focused on was this formula right here. It was basically when we took the limit of the sum of f of xi times delta x. And this we said was the formula for, we notated it as Rn, meaning this was the area under the curve using the right point method. Now there is another method. I mentioned three in the other video. I'm going to link a card up to. I mentioned the right point method, the left point method, the midpoint method, and there's obviously a lot more. Like there's a trapezoid method and a bunch of other methods. But another one that's worth noting is the sample point method, and the formula looks very similar to the right point method and all the other formulas actually. The only thing that changes is that, again, it's x subscript I. We're going to include this star right here, and we're going to keep delta x, and this is going to be a sample point method. So the only thing that changes is we note that there is this star. Basically, all that star is saying is that we're going to take a sample point within the xi minus 1 to xi interval. So instead of taking like just the right point or like the right upper corner as the point to draw like the rectangle, we're going to take a sample point on that interval and we're going to draw the rectangle from there. I'm going to go ahead and show you graphically what that means, so I'll be right back. So here's like a visual demonstration of what I meant by a sample point within this interval. In the right point method, we were consistently taking the rightmost corner of the rectangle that we were working on. So if it was this one, then we would take this point right here. However, for the sample method, what we're going to do is we're going to take that rectangle and we're going to take a sample point anywhere in that, and we're going to use that point to draw the rectangle. As you could see, sometimes the point, like right here, this third one, sometimes the point is all the way at the left, sometimes it's dead center, other times it's all the way on the right. Like, we just take a sample point within that interval, this interval specifically, and then we draw the rectangle using that. That's all the sample point is. So here is the definition of a definite integral, and you'll see why I brought up the sample point method. It's because it's going to be used in the definition, but it's very simple if we understand what the right point method and the left point method are. So the definite integral, we say if f is a function defined on some sort of closed interval a to b, then we divide this interval into subintervals with equal width. And like we remember, the width of each interval is going to be the length of the total interval, meaning b minus a, the two endpoints, divided by n being the number of rectangles we want in that interval. And then we let x0 equal a, meaning the start point is going to be the start point of our interval, and then we let x1, x2, so on, to say that xn is equal to b, meaning the end point of our interval. And then we let these be the endpoints of the subintervals, and we let x asterisk and then subscript 1 and onwards to n, these are the sample points. And then we constrained it so that x, the ith sample point, lies within that interval that we talked about. Then we say that the definite integral of f from a to b is defined as such. This right here is the definite integral that we're talking about. The reason it's definite is because we have these points, these start and end values. We'll go more into depth with them, but this is the definite integral. And essentially, it's like saying what we learned about the sample point method, which is right here. And the only thing that we need is that the limit of this function exists. If it doesn't exist, then we can't say that this integral exists. But a lot of the times it will, and we could say that these two are equivalent to each other. And we can also say that f is integrable on this closed interval from a to b. So a little bit more about the notation of the integral. We call this right here, this f of x, the integrand, and it's basically the function that's being passed through the integral, and we're going to be like calculating the area under that curve. A and b in this case are the limits of integration, and it's very nice because in the integral we could see what they are. So before we were saying, okay, let's find the area under the curve x squared would be the integrand, and then we would say from 0 to 1. So a would be 0 and then b would be 1. However, in the limit way of writing it up here, we didn't really see those limits. We would use it to calculate like the dx and xi, but it would never be shown in that like this notation. So the integral is really nice. We can see the interval that we're integrating on. So a is going to be the lower bound and b is going to be the upper bound. And then dx right here basically tells us the independent variable that we're going to be working with. And if you remember back in derivatives, I kept saying we're writing d over dx, and it's important to write that dx because it tells us what variable we're dealing with. Likewise in the integrals. Just remember that to leave that dx or dy, whatever variable you're going to be using, it's very important to know which one you're referring to. So a quick little theorem basically says that if f is continuous on some closed interval and f has a finite number of jumps and discontinuities, then f is considered integrable, meaning that this integral would exist. So the other quick little theorem, we kind of went over this. Basically, if f is integrable on this interval, then we say that this limit is equal to this integral. And I'm kind of going to give you a example. I'm going to relate it back to the previous lesson, and we're going to see how this form translates to the integral form. So let's go back to the example that we were using from last lesson. It was that we had this function y equals x squared, and we were trying to find the area under the curve between 0 to 1. So how did we do that, right? We said we were going to break it up into rectangles, sum up the area of the rectangles, and then make sure that the number of rectangles was a very large number, also infinity. So first we took the area of each rectangle, and we did that by finding the width of each rectangle, meaning delta x, and in this case delta x was 1 minus 0 over n, and this was the width of each rectangle. Then we also needed the height of each rectangle. So it was the function evaluated at xi, and xi in this case corresponds to 0 plus the width of each rectangle times the rectangles we kind of want to skip in this case. So it was equal to I over n. And we would get this formula that the area of the specific rectangle was 1 over n times I over n squared, because f of xi was going to be I over n squared. So we would get this formula for the area of each rectangle, and then we wanted to sum that up. So we would sum up all the rectangles by passing it through the sigma function. So it would end up something like this, and then we wanted to take the limit as n approaches infinity of all this. So this was the formula that we ended up getting to find the area under this curve. Now we could see how this would translate to an integral now. So firstly we would include the integral sign, and after that we would include a and b. And a and b are our bounds of integration. So in this case we're integrating from 0 to 1, so our lower bound would be 0 and our upper bound would be 1. Now f of x, I said, was the function that was going to be integrated. And it's really nice because here in this limit one, we need to kind of compute it in this step right here. But in the integral way, like in the integral notation, we don't really need to compute anything. We just need to write the function. So we can just write x squared there and it's fine. And also we want to keep track of which variable we're going to be differentiating, or sorry, taking the integral of. So it will be dx. And that's it. This is all there is to integral notation. You could see how much easier it is compared to finding out this whole limit. Now, this limit is kind of how the computation goes in the background, but this integral notation is a lot easier to read, and it's much more pleasant to see compared to this one. Now moving on to evaluating integrals. As of now, we don't quite know how to do it yet, apart from using the sigma function. And so because we're going to be using that, I'm going to go over quickly a few rules and properties of sigma notation. So I'm just going to quickly write them down and then we'll go over them. They're pretty easy. here they are. Here are 7 rules basically that we use to evaluate these integrals. Now the first 3 are just common sums that we see, and we've already bumped into this one, I believe, but this one is even more famous, and I'm pretty sure like everyone should kind of know all of these. They're not too difficult to memorize, especially the first and third one, but the second one maybe. But yeah, it's just good to know these for evaluating these kinds of integrals. So the sum from I equals 1 to n is just this formula. The sum of squares from I equals 1 to n is this formula, and likewise for the sum of cubes, it's just this formula. Now moving on to the more like simplification properties in a sense. If we have the sum from I equals 1 to n of a constant, all we're going to do is just take that constant, multiply it by whatever n was in this case. If we're taking the sum of a constant multiplying an expression, then we can just bring that constant outside of the sigma sign because it's not dependent on any of the variables, especially I. If it's not dependent on I, we can bring it out of the sigma function. If we're trying to take the sum of 2 functions or 2 expressions that are being added together, we can split that up into individual summations. And likewise, if we have the difference of 2 expressions, we can split that up into the difference of 2 summations. So this one and this one. So they're all pretty simple. This set of properties, it's applicable in other areas too. We saw with like derivatives, and we'll see with integrals too that it's fairly similar. So these you should kind of like know by now. So here's a sample problem that we might encounter when dealing with these types of questions. We're asked to evaluate the Riemann sum for this function taking sample points to be the right endpoints, and we're given these constraints. So the start is at 0, the end is at 3, and then the number of rectangles we're going to have is 6. And then the second part of this question asks us to evaluate this integral. And if you see, these 2 questions are looking very similar. So we're going to go through a step-by-step solution for both of these. So the Riemann sum, maybe I haven't mentioned this, but the Riemann sum is basically just what we were doing in last lesson. It was finding the area of the curve just by adding up these rectangles. So the process is going to stay the same. It's just they kind of decided to name it Riemann sum instead of find the area of the curve, but they both mean the same thing. So we're going to start off by finding the area of each individual rectangle. How do we do that? Again, we find length and width. We should be pretty good at this now, so I'm going to skip forward. So here is the width of each individual rectangle. And now if we take a note, we are being restricted on the amount of rectangles that we have. So we're going to have something like x1, x2, all the way to x6. And the way these intervals are going to be broken up is we know that we're taking the right endpoint. So we're not going to start at the initial value of a equals 0. Instead, what we're going to do is we're going to start at the next value, like we know from the right, because it's the right endpoint. So if you go back and watch the video that I made on areas under curve, you'll understand why we're starting not from 0, but from the next value. I'm going to link up a card to it right now. But essentially, we're going to start from a half, and then we're going to be moving on by like the same width, which is a half. So we will end up getting these intervals as a result of this. And as we can see, there are 6 intervals here, and that corresponds to these 6 rectangles. And again, we stop at 3 because that's our endpoint. So now we don't even need to make any further computations. We can just write the Riemann sum, which was this, and it was f at xi. They were asking us to take sample points of the right point, and now we can just fill in what we know. N is going to be 6 because that's what they told us in the question, and over here we are going to have f of xi delta x, and we can get rid of this sample stuff because we know what the points are going to be now. They're going to be in this like array of values. So now I'm just going to write out this Riemann sum in total. I'm not going to evaluate it as a sigma thing, just so everyone can see what's going on. So there we go. We have summed up the area of each of the rectangles within this interval right here. Now what we can do is I'm going to go ahead and factor out a half and then evaluate each of these function notations. So there we go. We have found the area under this curve using 6 rectangles using the right endpoint. Now moving on to part B. They asked us to compute the integral from 0 to 3 of the function, which was x cubed minus 6x dx. And we can compute this function using what we know about the Riemann sum and how it relates to integrals. So firstly, let's figure out what a and b are. A in this case is 0 and b is 3. And so having known these two endpoints, we can figure out basically the width of each rectangle and then kind of the formula for xi and slowly transition it into a Riemann sum, because as of now that's the only way we know how to solve these integrals. So let's figure out what delta x is. So there is the formula for delta x, and the formula for xi is going to be here. So there it is. We have figured out what delta x is, and we have figured out what xi is. So now we can slowly start converting this integral into the Riemann sum that we know. So there we go. I have filled out essentially all of the knowns, the stuff that we figured out. We figured out xi and delta x, plugged them in, and now we have a very familiar formula that we are good to work with. So I'm going to go ahead and start solving using this sigma notation and the stuff that we've learned about sigma notation. So firstly, I noticed that this term right here is not dependent on I, so I can bring it out of the sigma notation. So there you go. I've brought out the 3n term, and on top of that I have eliminated this function notation and plugged in the values into our function. Now I'm going to go ahead and simplify by expanding the powers. So now, as we can see within our summation, we have the difference of two terms, and like we saw previously in the properties of the sigma function, we are going to break this up. And now I notice that there are a few terms that are not dependent on the variable I, so again I'm going to bring them out of the sigma. So there we have it, and now we are left with these two expressions, and as we know, these expressions we have seen the answer to them up over here on the sigma part over here. So these are actually going to be property number 1 and 3. So I'm going to go ahead and fill these out. So now that I've expanded this, I'm going to go ahead and bring this term inwards. So now I'm going to bring this power inwards and expand. Now I'm going to remove common factors. Now I'm going to expand the numerator here. Now I'm going to force factor the top, the numerator, to cancel out the denominators here. Now I'm going to cancel out the denominators and numerators. And now this becomes a simple limit that we know. So this right here will be a 0, this will be a 0 once we plug n equals infinity, this will be a 0 as well. So we're just going to be left with 81 over 4 times 1 minus 54 over 2 times 1, which is just going to evaluate to 81 over 4 minus 27, which is equal to minus 6.75. So now we can see, looking back up here, before we were getting minus 3.9375, and now we're getting negative 6.75, and this is the value that it actually should be. So we can see how big of an error we got. On to the last section, we're going to talk about properties of definite integrals, and there's 7 properties here. I feel like they're pretty straightforward. I mean, like some of the sigma properties actually like kind of mimic these ones, so it should be pretty straightforward from here. I'm going to go ahead and write them down, and then we're going to talk about them real quick. So I've written down 7 properties of definite integrals, and I think they're going to be pretty straightforward, but let's go ahead and talk about them. So the first one is that, oh, right here, I forgot the fx dx. So firstly, if we have the integral of a function, right, and then we switch the bounds of it. So before we had the lower bound was a, and now the upper bound was a, and before the upper bound was b, and now the lower bound is b. So if we switch those around, all we have to do is throw in a negative sign in front of that integral. And the explanation for it is pretty simple. Before we had delta x was equal to b minus a over n, right? And we knew that b was going to be greater than a because b was the end point basically of that interval. So b was going to be greater. But now the way we do it is that delta x is going to be a minus b over n. But b is the greater value and it has a negative in it. So this whole term is going to be negative now, and the integral is basically going to have this negative introduced to it. Now the second formula also comes from a similar like background. Basically, if we have the integral and the bounds are both the same, the integral is going to value to 0, and we can see why. We had the delta x, the width of the rectangle, was going to be b minus a over n. However, now we have it such that it's a minus a over n, which is equal to 0 over n, which is 0. So the rectangle's width is going to be 0, meaning we're not going to have any area. Now this one right here, we have the integral of just the constant function. And this right here will make absolute sense to you once I kind of just draw a quick little plot. Let's say we have this axis, and then we have our constant function. We'll call this y equals c, right? And then we're given 2 bounds, a and b. This is a, this is b, right? And it's saying find the area between these 2 values under this function, right? Well, it's pretty obvious. The area under this this graph right here between these 2 intervals is just going to be a rectangle, right? The width of it is going to be b minus a, and the height of it is just going to be the function, which is c. So this is how this formula becomes. The fourth one, again, this is what I said about it being like similar to the sigma stuff. If we have the addition of 2 functions with an integral, we can just split it up. Likewise, if we have a constant within our integral and it's not dependent on like the x value, then we can just bring it out. Like number 4, number 6 is just basically the difference of 2 functions right here. We could split that up into 2 integrals. Now the last integral is it's pretty obvious, but maybe you haven't seen it yet. So if we have the integral from a to c of a function, and then we have the same integral, however the bounds are from c to b this time. In this case, if it's the same function, and we see this kind of like chain, so the upper bound here was c, but the lower bound here was c, then we can just say that this is the integral from a to b of that function. And I can quickly show you why. So let's say we have a function that, I don't know, goes something like this, right? And then here are 3 intervals, let's say. So this is going to be a, this is going to be c, this is going to be b, right? The first integral, this one right here, is asking us to find the area under the curve between a to c, and it's this one, right? Then the second integral right here is asking us to find the area from c to b, so it's just this one. But we can simplify this and just kind of find the area of this entire thing all in one shot by using this integral right here. That's all this is saying, that we can, if these bounds are kind of continuous, then we can just combine it into one integral. So that's it for definite integrals. I hope this video helped. If it's helped you out at all, please like and comment as to what it's helped you out with. Like usual, if you're new to the channel, please like, comment, and subscribe. It's greatly appreciated. And yeah, I will catch you guys in another video.